Yes. And then, see, it's
Okay, let's get rolling. Actually, today I think I'm a little early, but we'll go ahead and start. Where did we get to last time? We were kind of finished up all the stuff, but I was just starting to work a problem, right? So we'll go through that problem, and then I want to do it by hand, and then we're going to do it in SAS. And I'm going to prove to you that SAS almost matches. I had hoped to say SAS matches, but it isn't exactly because, and our author warns you of this in the reading, that different software use slightly different, like those constants, the C4, C5, slightly different values of those, or different formulas for computing things. But remember the setup here. We have past data that we've been monitoring a process. So we have some kind of an estimate of mu, which is the mean of the process, and then an estimate of sigma, right? And then once we're not going to do it today, but you use that past data. Then remember we talked last time that you then remove you start with the S chart, S for standard deviation, and you remove samples that were weird on the variability. Then you use the remaining samples to figure out your estimate of mean and all that, right? And then you make your charts and track them forward through time, right? So we're going to go back to the example that we had started with last time, and there it is, all done in SAS, but I don't want to go there yet. So here was the data. Let me do that so you can see the whole thing at once. And you remember what the scenario was? Remember what this data was about? We had the chunk of aluminum, and we were measuring the density. So it's a machine that's used to measure density of bones, but these aren't measuring bones. The observation 1, observation 2 is measuring this chunk of aluminum of known density, right? So they take 2 readings before they start measuring patients for any given day. So day is what we call the subgroup variable, or it identifies the samples. So this is sample 1, sample 2, or whatever. So that's day, right? So then my n for each of the samples is only 2. I've got 2 readings. So then the mean of those 2 numbers, so this is 1.261, 1.260. The average of that is 1.2605. The standard deviation of that is 0.000707, and so on. So you got 30 days worth of data. You got 30 X bars, and you got 30 standard deviations, or S's. Right? Now, remember from your notes, let's see, I want to go back to this thing. Remember from your notes the S chart has a center line at what? Do you remember? Center line, and then upper and lower control limits. So if we start with an S chart, what'd you say? That's when you're out of control. But I'm just trying to set up the chart. So remember, in a chart,
C sub 4 sigma, is that right?
Okay, that's right. So the center line is C sub 4 times sigma. But sigma is an unknown quantity, so you have to estimate it. Right? And this is scratch paper over here. Sigma hat, that's not a very good equal sign. Sigma hat is equal to, you remember how the S's from the samples, how we use them to get sigma hat? And it involves this C4. But basically what I'm trying to get to is that this center line is S bar. I made it look like a fraction, but S bar. And so what do we mean by S bar?
The average of the standard.
The average of those 30 standard deviations, right? So if I put in sigma hat here, I'm trying to show how these two relate. To get our estimate of sigma, which I really don't need to do the center line, I just take S bar and I got it. But we're going to use sigma hat later. So sigma hat isn't C4 times S. What is it?
S over C4.
Right. S bar over C4. Okay? And then the upper limit, upper control limit, you remember the formula for that?
3 times the C4 sigma.
No. So I was joking, I nodded when I said no. You're right for X bar chart, but not for S chart.
Mean of S plus 3 sigma S.
It's like B6.
Yeah. It's one of those constants. It's B6 times sigma hat, right?
So is B6 always the same number, or is it?
I'll show you in just a second, but it depends on the sample size of your
When
sample.
we get it from the chart.
And we get it from a table. Okay. So the upper limit is B6 times sigma hat. Right? And what is the lower limit?
B5.
B5 times sigma hat. And with this marker, my 5 kind of looks like a 6, but I guess I better clean that up. Okay? So, we'll go to the table in a second and see what these constants are. But let's go back to the spreadsheet and get the value of S bar. And that's the only thing that's appearing in here that's dependent on the data, right? We start with S bar, we divide it by C4, we get sigma hat. S bar will be our center line, and then this multiple of sigma hat will be our upper and lower limits, right? So we need S bar. So if I go back to the spreadsheet, what I have done here is I've just used Excel formulas to compute the mean of these 30 values of the standard deviation. And down here at the bottom, it's 0.002805. And that's only showing, I actually want to show one more accuracy just to get closer to SAS. I found that if I have, let's see, how do I get my, I guess I got to do this, right? Show capture commands. So, escape. I want to increase my number of decimal places by 1. So you get 0.0028048. And so, I guess I got to use my mouse to get back to the other machine. You guys wrote that down, right? My memory is not so good anymore. Point, read it to me.
0.02808.
048. Okay? So now I got S bar, I need this C4, and that's a constant that corrects for the bias in averaging standard deviations. Remember that was a biased estimate of sigma, so to correct it, you divide by this constant. Right? So, here is the table that shows what those constants are. So in this, the actual table, if you go to the textbooks on quality control, this table will get much bigger than this. But most of the time, your samples, remember what numbers I threw out in the very beginning? It's usually
Like 4 or 5.
4 or 5. So usually it's 4 or 5. This particular example we're using, it's a 2, so we're at the very top row of this table. All right? So C4 is 0.7979. Got that memorized?
Yeah.
Okay, so let's go back to here. And sigma hat is this number divided by 0.7979. Right? So take that on your calculator and tell me what you get.
0.003515.
003515. Okay? So I need to erase a little bit here to clean up. So my notation is bad here because I was kind of crunched, but I said S bar is this, and then this is C4 on the bottom. So when you divide the two, you get this number. Everybody following me? Okay? But S bar, the top of this fraction, is my center line. So if I draw my center line, then on the y-axis it'll be at S bar. 0028, and I'll dispense with the rest of the decimal places. Okay. Then the upper limit, upper control limit, is now B6 times that sigma hat. Right? Oh, we need B6. So let me make a place for it here. B6, go back to the table. Samples of size 2. B6 is 2.606. Now, what about B5?
That just means it's 0.
That means it's
You can't go below 0. Right?
So, B5, when you have such small samples, clear up to samples of size 6, that B5 is always 0. Right? Well, if we go back to the plot, B5 times sigma hat, if it's a 0, then the lower limit is 0. Right? So we don't, for this particular problem, we don't have to deal with that. If we have bigger samples, 6 or more, then you'd have a B5 constant that you would also multiply. But B6 is 2.606, did I remember that right? Times sigma hat. Since I don't have room to write it in there, I just put a little arrow. So tell me what that works out to be.
0.00916.
00916. Okay? So I got to get my graph right over here. And if this is 0.0028, which is about 003, this one is about 009, I need to be 3 times that high. Right? So you can already see I'm going to run out of room. Right? So if I take this distance, there's twice as high, 3 times as high. There's my upper limit. Right? So I'm going to hit page down, I'm going to redraw it so I have the whole screen to do it. But everybody see what I'm doing? Okay, so this is at 0.009. Alright, so my S chart, if I have a center line here, and that was at 0.0028, and then that would be about 006 and about 009, so 0.00916. Is that what it was? And then I'm going to draw a dotted line there. Okay? And my lower limit, so I'm going to write UCL up there. This is my CL for center line. And then the axis is actually my load because it's 0. And since we're plotting our standard deviations in here, standard deviation can't go below 0. So you know you're never going to go out below. You can only go out above for such small samples. Question?
So this might be kind of related. Does Six Sigma fit into this anyway?
Yes, it sure does.
Okay.
Yep.
Are we going to talk about that? Or
Yeah,
is
I'll
that
talk
something
about it.
that-
I'll talk about it today if you remind me.
Okay.
But it doesn't apply to this, to an S chart, it applies to an X bar chart.
Okay.
Because that's your plus and minus 3 sigma. Yeah, and you may have heard that term. This is a 6 sigma thing, right?
Like a lot of jobs have, like you need to be a Six Sigma black belt is what they call it.
Yeah. So this whole, I guess I'll talk about it now. This whole 6 sigma thing came up in the last probably 15 years maybe. And it's a quality thing, right? We want our employees to be quality minded. So they give them training, and it's called 6 sigma training. And that's where it comes from. It's like, well, 3 sigmas above, 3 sigmas below, that's a total of 6 sigmas, and you got to be within that, right? So they give them training, and it's like stages of training. So once you've had all of the training, you're a black belt in 6 sigma. You're supposed to never do anything wrong.
Okay, so the employee is within 3 sigmas up and 3 sigmas down. So you personally are supposed to be within that Six Sigma thing, not the work the products you're producing.
Is that how it works?
I have no idea.
I don't know. I've never looked into that kind of training, but that's all I know is where the name came from.
Okay.
But that's exactly where it came from. Okay. So now we have our graph here. Let me just label this 0.006, and that's 0. I'm going to flip back to the spreadsheet, and we're going to plot the first few of these points. Okay. So the first point is 0035. We'll go to 4 places. The next one 0042, and then 0007. You got those memorized? Better yet, written down? 'Cause once I go back, I'll never remember those numbers. Got them?
I'm just wondering, so when you start doing it though, like so if you start with day 1 or whatever, then just go like across, right?
Right.
So we were starting with day 11.
Oh, thank you. I didn't notice I wasn't scrolled to the top.
I mean, it wouldn't necessarily
Yeah.
matter.
No, you would
It's the
start at
process.
day 1.
Okay.
You would start at day 1. I have 30 days, and I just didn't realize that I had scrolled off the top.
No, yeah.
So day 1, we got new numbers to memorize. This is point 0007, and then 005, we'll call it, and then 002. Got them? Okay. So down here, this axis is the day axis. So it's whatever your subgroup variable is. And so that's the term that SAS uses, your subgroup variable. So my subgroups, or my samples, are based on day. So this is day 1, day 2, so on up to day 30. So read to me that first one.
Like 0007.
So 0007, which is it's pretty low on this chart.
So
Right.
it would be a fourth of the way up.
Yeah, it'd be about a fourth of the way up there. So we'll put a dot right there. Okay? And what was the next one?
0.005.
0.005. This is 003, 006, so it's up about right in there.
Two.
And then 02.
002.
Oh, 002. Okay, so that's, yeah, just a little below that center line. Okay, and then you would connect the dots. Not that it's important, but it makes it easier to find the dots and see any pattern, right? And so and you do that for all 30 dots, right? And then see if any of them pop out. Okay, so I will show the SAS graph. And the S chart is the lower one. So we'll look at it first and then we'll go do the X bar chart. So here are the same three first points that we just graphed by hand. The upper upper control limit, it marks at 009. Hey, it fits, right? If you tell SAS to give me more decimal places of accuracy, which I couldn't get it to do it on the graph, but I could get it to output the values, and it's not exactly the same number. It's 0092 something. We got 00916. But we've got some round off error in our S bars and all that SAS isn't doing. Plus it uses slightly different values. And I may have written in my notes here. Oh no, actually I wrote in my notes, SAS says 0.00916. Isn't that the number we had? Exactly. Okay. And the number that I had computed by hand is slightly different. It's 00928, but that's because I bet I have something wrong, because I have a different, and when you said, remember the 003 thing for sigma hat? I had a slightly different number there, but I bet I have all the same numbers entered. I bet I just, when I did it by hand, I probably had a little bit of an arithmetic error, which is why I wasn't quite matching SAS. Lower confidence limit was 0. We knew that. And then S bar, it puts the center line at S bar, and it says equal 0.003. And so it's rounding to just 3 places, which we have 002848 or something like that. Right? Now interpret.
The variability of the symbol is not out of control. It's in control.
It seems to be very in control. Yeah.
Do we do like the runs of 9 test on this one?
You sure do. Yeah. So it looks to be in control. Do you see any runs of 9 in a row above the center line or below the center line? No. Here's 4, but then one right on the center line. You could almost count that one as a 5. That one, if it's just a tick above, that'd be 6. But that's the most you ever see. Right? Yeah.
And why would you care if your variability was below center line?
Yeah, you wouldn't. If it was below the center line, especially if it looked like it was trending down, that's a good thing, right? Your variability is getting less and less.
Okay.
So I doubt I would stop the process and say, hey, I got to fix something because my standard deviation is out of control if I'm going down. But if it's trending up, you get 9 in a row, then you would want to flag that. And obviously none of them clicked above the upper limit, and so nothing gets kicked out there. Okay? So now, the X bar chart, you can see what it looks like. We'll come back and interpret it in a minute and look at these numbers, but let's see how to compute them by hand. So the first thing we got to do is figure out the center line. So X bar chart. I'm trying to save room over here to do all the calculations. Look back in your notes. Where's the center line of the X bar chart?
X bar.
X bar bar, which is our estimate, our best estimate of mu. So that's also often written as mu hat. Right? So it's an estimate of mu. And then I know that Nate knows the rule for this one because you started to say it before. So what's the lower control limit?
Let's see, I have to look at my notes because you freak me out. Someone else got it. Go for
So
it.
it's mu, the lower is a minus, but -3 sigma. Now, I don't know what mu is, so I have to estimate it. And I don't know what sigma is, so I have to estimate it, right? So sigma hat over square root of n. And what's our n? 2. So I'm going to go ahead and write the n, just so it's the whole formula. But we'll substitute in the numbers as we get them computed. So then the upper control limit is the same thing, but with the plus sign. Okay? So we'll go to the spreadsheet. We'll get x bar bar. And we'll go back to the page of notes where we computed sigma hat. Then we'll plug it all in and see what we get. So let's go to the spreadsheet, which was here. So here, the title of this column is mean, so that's x bar from each sample. And I want x bar bar, which is the mean of the means. Okay. So scroll down, and x bar bar, see how I wrote it out? I couldn't figure out how to get 2 bars over it. X bar bar.
You can only do it in equation though.
Yeah, with 2 bars though,
Yeah.
So then 1.2619. Got that? 1.2619. So we write that here. X bar bar is 1.2619. And then remind me what sigma hat was. We took S bar, we divided by C4 to get this sigma hat. We did it on
0.03515.
0.03515. Right? Okay, here we go. Center line is just x bar bar. So at 1.26, that looks to be exactly right there. So that's 1.2619. Kind of ran out of room, but that's what that says, 1.2619. And then lower limit. 1.2619 minus 3 times that number, so I don't have to rewrite it, over the square root of 2. Tell me what you get.
$1.232.
232?
I got 1.2544.
Okay, that's what I got.
Okay. I must
Did you do the divide by square root of 2?
Yeah.
That's kind
Okay. I said I did.
I think I broke this thing.
Yeah.
I'm trying to lower this so
I
you
got
can
the
see
same.
through. Is
I
this
got
in
it.
your way?
No, I'm good.
Okay. So 1.2544.
Yep.
Is that what you said? Yeah. Okay. And then do the upper control limit. I won't write it all out except the answer, but it's the same exact thing but with a plus sign. So you can do second function enter on your calculator.
1.2768.
1.2768.
No.
No.
What?
It's 1.2694.
So if you don't learn anything else all semester, learn don't trust Nate's
What?
calculator skills.
And also don't trust it around there.
His rounding. I'm going to trust the 2.
Yeah. 2694.
26, that's what I have in my notes. 1.2694. Okay, so upper limit 1.2694. This is about 1.26. And so, well, 262. and I need to get to 1.269. So 262, 3, 4, 5, 6, 7. That's too many. 1, 2, 4, 6, 8. So it'd be about right there. 1.269. So I'll draw a dotted line across there. There's my upper limit. And then the lower limit is at 1.25. So if I go, let's see, that's 262, 26, 258, 6, 4, 2. It's 254, so it'll be right there. It should be symmetric. And my picture, if it's not symmetric, it's just my artwork. But I think that's pretty beautiful. Doesn't it look right? So my writing ends up on this dark blue, so it's kind of hard to read, but 1.2544. Okay, so far so good. Now what do we do? Okay, we go back to the spreadsheet and plot the points. So I need to scroll back up. So let's write down the first few of these. We're writing the means this time. So write them down for me. 1.2605, and then 1.2645, and 1.2595. Got those? Okay. Can't get back to the screen without the mouse. Okay, so what was the first one? Day 1?
1.2605.
2605. And since this line is 261905 would be just right about at that first tick mark that I made. So right about there. Okay. And then the next one?
1.2645.
2645. So this is 262, 264, halfway in between, about right there. So that's day 2. Day 3. 2595. So that's really close to this one was 2605. So it's just a hair below where that point was. So that's day 3, connecting, and so on for 30 more points, or 27 more points. So I'll have you do this on the test by hand with 30-some points. Yeah, it wouldn't work very good on a test, but so mostly on a test, you'll see pictures and be asked to interpret. I probably wouldn't make you plot the points in there. So I'd have one problem that makes you compute what these numbers are. The center line, upper and lower limits for both. And then another one where I just give them to you, different scenario, and say, what do you see here? Kind of an interpretation thing, right? And not actually plot one all the way out. Okay? So let's compare the numbers that SAS computed. And SAS calls them the 3 sigma limits. So upper control limit 1.269. What did we have?
1.2694.
2694. So rounding to 3 places we match SAS. Center line 1.262.
2619.
So that rounds, that's close. And then the bottom 1.254. We had 2544, right? So really, really close. Okay, now the $40 question. How do I make SAS do this? Because I will have a homework assignment for you. You won't obviously have to do it on a test, but you'll have a homework set where you'll take one of these data sets and produce all this, you'll use a combination of Excel and SAS. Question?
Is it just like the same interpretation, I guess, in control? That's all you need to say?
It is, that's right.
Okay.
The X bar and the S both have the same way to interpret.
Okay.
You got your upper and lower limits, and you're seeing if anything goes out. With the exception that common sense told us that, well, if it's the standard deviation chart, going below the center line is really not working. So I don't know if the book ever says that, but I certainly wouldn't worry. If I got 9 in a row below, I wouldn't worry about it. But if you get 9 in a row above, that probably means you're trending up, and it's time to say, hey, we're heading for disaster here. Let's fix it.
Can you elaborate a bit on that? If this is a test to figure out if the machine is in calibration for bone density, and somebody has low bone density, and you're comparing this to a hunk of aluminum, and it's saying that the aluminum is lower than what it should be, then you're basically throwing the results of they don't have low bone density.
Now remember though, this is an S chart.
Right.
This is showing, we got a classical.
Oh, I'm sorry. Pardon me.
You can join if you want, but I'm just warning you, you might be bored. This is a standard deviation,
Okay.
right? So if the standard deviation, if I take 2 readings on my chunk of aluminum, and they are always dead on, so that both readings are exactly the same, it's going to have standard deviation of 0. That doesn't affect my measurement of. This is the one.
I just needed to visualize what we were actually describing here.
So this is variability in my
If it's
multiple
got really-
measurements of the aluminum block. How variable are they?
And if it's got really low variability, that's good.
Yeah.
Okay.
Now, yeah, and low variability is always pretty good. But if I'm making ball bearings and I'm measuring the diameter of those ball bearings, right, then again, low variability is good, but it's a little bit different than just making multiple readings of the same thing. And is my reading device consistent? But
Thank you.
okay, so now look at the chart. Obviously nothing pops out above or below the mean. And what about the runs rule?
It's good.
Yeah, there's not 9 in a row above or below the center line. And now below the center line would be a concern. I'm measuring their density too low, or I'm measuring their density too high.
So would the exact interpretation of the X bar chart be the averages of the 2 samples across the 30 days is in control?
Right. And that's a measurement of calibration. Right. So on day 1, we took a block and we measured it and we got this reading, and that's close enough to what it really is that we're in control, and we stay near that target. Right. But I know your question. Go ahead.
Oh, I was gonna ask, like, what is the actual range that's good? Like, if they read your bone density, what's the range they look at? Just so I kind of understand, like, how much variability and the importance.
Oh, when we switch from measuring aluminum to measuring bone?
Yeah, like, what range do they look at? Like, between what 2 numbers are good?
Yeah, I actually don't know. I don't know, and they don't discuss that in this example, but so I don't know. The numbers probably wouldn't be anywhere near 1.26.
Yeah.
This because bone is probably less dense than aluminum. So the numbers would probably be down. So I don't know the range that would be clinically significant if you're above this or below this, right? I'm not sure on that, but this is just checking our calibration of our instrument. Is it measuring a known quantity like it should? And if it starts to drift, then you're getting out of calibration. You need to reset. That's the idea here.
Are there any exceptions? So if you, instead of like 30 days, if you have like 100 days and there's only 1 point in 100 days, you just happen to pull a bad sample, is it still out of control, or is...
1 point out is out of control. Now, but the way you as a company react to out of control can dictate, well, what do I do? If I'm looking really good and all of a sudden, boom, 1 is out of control, what's the first thing you do? We talked about this when we introduced this topic. You look for a blank cause, special cause. Was there something on that day that would explain why it popped out?
Like a power shortage or
Yeah,
whatever.
like the lights went out, and so the machine was shut down and had to boot back up or something. So, you know, whatever, anything like that, then you don't worry about that point being out. You've identified why it went out, not an issue. But if you can't figure out why it went out,
It's probably a calibration issue.
yeah, there's probably something going on you need to look into. If it went out that day, your decision may very well be, well, let's see what happens tomorrow. And if tomorrow looks fine and the next day looks fine, and it's like, well, something weird happened that day. I couldn't identify what it was, but I'm not going to shut the process down to try to figure it out until I get more problems and it looks like this is a recurring thing. Right? It depends on what it is you're doing. And it's not the statistician making those decisions on their own. It's the whole manufacturing team that gets together and says, hey, what do you think? Let's make up some rules here.
So if I were to redraw the X bar chart, and it kind of started over there normal, and then it kind of went up, and then it went down below the bar, and it went up again, and then it went down again. Would you interpret that as that it has a tendency towards drifting upward?
Well, yeah, you could interpret it that way. Like here, it almost looks like there's a pattern where it drifts up. Like we've got, starting with this point, it's going up, and then it starts down, and then it starts back up, right? And you get quite a few in a row. In time series, we would call that autocorrelation. Like where you're at this point seems to depend on where it was the point before. And as long as you're staying within, then it's probably not a concern, and you don't get more than 9 in a row before it turns back. But you know, if you're measuring density of a chunk of aluminum, maybe atmospheric conditions can affect it, and so you have low pressure come in, and it'll register low for a while, and then you get high pressure, and it could tend to drift. But
I was thinking like maybe they would calibrate it. They were calibrating it in between those rises so that it would be low again, and then it would rise again, and then they have to calibrate it low again, and then it would rise again, and that the machine may be failing because it has a tendency
right,
to drift.
and that's your, you wouldn't scrap the machine until you hit 9 in a row drifting.
But it would kind of indicate if you, even with their calibration, that if you didn't do anything,
It would have
just
kept going.
definitely looks like the machine is failing.
Yeah, so this machine would be defective. Okay, so now let me go back. This is within SAS, and let's show you how to do it within SAS. So what I need to do, I need to go back and I need to go back to my spreadsheet, and I've got it prepared, but to save time, because I'm kind of running out of time, SAS will not like the data set up in this way. Did I talk about this yet? You don't want the two or the multiple observations from a single sample on the same row. What you want is, can't write on my
You want
screen.
it transposed?
Yes, you want it transposed. That's exactly what I want. So what I want, let me come over here. You want a column with day, and then 1, 1, and then 2, 2, and then what's that varied density? So density, then you'd have your 1.260, you know, whatever. So it's broken like that. So the SAS is only looking at 2 columns. It's looking at a day column, and it's looking at a density column. And then the first time that I ran it in SAS, I got an error message that said input data is not sorted. So here's the data after I reconfigured my spreadsheet. And I just did it with cutting and pasting. You could do it within SAS, but you really can't do it without some SAS programming. But I reordered the data, but I had, let's see, I think I had days 1 through 30 from the first reading, and then days 1 through 30 for the second reading. because I just copied that column and dropped it below the other column, that's the easy way to do it in Excel. But then you want to sort by day. Probably it's easier to do it in Excel before you come into SAS. But SAS is pretty easy. Once you get the data read in, you can click on tasks and then data and then sort data. And it'll say, what variable do you want to sort on? Sort on day, boom, it's done. Okay. It's already done for me, so I don't need to walk you through that. But so then, I have the data set up the way I want. Click tasks. Then down here it says control charts. So click on control charts. And then this is mean and range chart. Remember we talked about that and said, that's kind of old-fashioned. Most people won't do that. Mean and standard deviation chart. That's S for standard deviation. So that's the one that we've been doing. So I'll click on that, and then up pops this screen. First I have to tell it what the data is. So density is the thing I'm measuring. So that's my process measurement. So I can take density and drag it over to there. Maybe. There we go. And then subgroup identifier. And remember I said SAS uses that word subgroup the way we use sample, right? So the subgroup is the sample. So that's my day variable. So you can either drag it or you can hit the arrow button and then tell it that's my subgroup identifier. Right? So see how that's set up? Then you can actually choose different ways for different options for what the control limits are. The default is the one I already showed you. So it defaults to doing what the textbook describes. Sigma limits, its default is 3 sigma, but you could change that to 2 or whatever. And then it says compute the control limits from the active data. So this is that discussion we had before about you use past data to give you the estimates, and then you set your control limits using that. Well, then you would compute from a selected data set, and you'd have it go read that data set, compute them, and then apply it to the new data set. You won't need to do that on your own. You do like the one we just did where we used it within the active data. Okay? Or you can specify. You can say, I want you to use these limits. Just tell it what they are. So default there. Tests, there's nothing really to talk about there. Then the next thing here says appearance, and you can try to make it pretty. If you don't like the colors it uses and the type of axes and all that, I wouldn't worry about any of that stuff. You could draw reference lines on it. You can tell it to draw a line at every tick mark, and then you'll get a darker line at the control limit and that kind of thing. So everything from there down is just beautification. So really, after you set the data, you're really ready to hit run. So you hit run. It thinks for a while, and then it produces the chart for you. Okay? And then you can take a screenshot of that, paste it into Word or whatever. You're going to highlight the numbers. I'll probably have you compute them by hand to verify that you match what SAS gives, like we did in class. Any questions? Can you believe that? I got done on time. About that. All right, we will see you Monday. Have a great weekend. And before I leave